Swayam Prabha. Digital India. Educated India.
Good morning everyone, welcome to the today's class. This is continuation to the last class. We have seen motion of liquid droplets in small channels. So let me recap what we have done in the last class. So in the last class, first we explained what are the applications of Stokes flow, and then we focus on microfluidics. Then we talk about specifically the droplet flow problem, that is what this motion of liquid droplet in small channels. Then we have established the governing equations and boundary condition, and then we have converted into one useful form. So these are the final set of equations we need to solve. So today's class will be mostly mathematical, so we have to do the derivation part. So in last classes we saw all the physical insights from, so in meanwhile wherever possible we can get physical insights. So this class mostly mathematical one, and these are the final expressions we need to solve. If you see our governing equations are fourth order equations, two to second order equations, and we have 8 boundary conditions, means our system is fully specified, so we can solve the system easily. If you have anyone have doubts till this part, you can ask now, otherwise we will continue in this lecture. Rather than solving a fourth order equation, we will solve 2 second order equations in psi and omega, and then we will get final solution in the form of psi. Okay. So first I am starting with my E square omega equal to 0. This E square is nothing but dou square of dou by dou r square of omega plus 1 by eta square by r square dou square omega by dou eta square equal to 0. So if you remember, in Stokes flow over a solid sphere, we consider directly the solution form is the solution psi equal to f of r times sin square theta. If you remember, this is the form we have considered, but in this class we formally derive entire derivation from using method of separation of variables, and we will see and what conditions the solution will becomes into this form. Okay. So now using method of separation of variables, I am assuming my sigma to be r of r into h of eta. So if you substitute this expression, this is only a function of r and this is only a function of eta. If you substitute in this expression, it will become h of eta into d square r by dr square plus 1 minus eta square by r square into r into d square h by d eta square equal to 0. If you rearrange this equation, you will end up with 1 minus eta square by r square into d square h by d eta square into 1 by h of eta equal to 1 by r times so this is the form you will get. If you observe this equation clearly, this entire equation is a function of eta and this right hand side is a function of r. Since these two are functions of different variables, this should be equal to some constant. So the question is, in which direction we have to take the eigenvalue. If you see the boundary conditions, neta boundary condition, if you see this eta boundary condition, you have homogeneous conditions. So, we have to take our eigenvalue in the direction of homogeneous boundary conditions. So, we have to consider eigenvalue in the direction of eta. So, here I am taking minus alpha square. From here you will get two equations. This is one equation, and these two equations we will get from our method of separation. So, what we have done till now is, we have a partial differential equation, we use method of separation of variables and we convert that partial differential equation into two ordinary differential equations. Clear everyone? Now, we will solve first this equation and we will find eigenvalue, and then we will solve this equation. Okay. So, I want to take a small transformation such that this equation will become a known equation, which is called a legendary polynomial. So, to doing that, I am taking a substitution y equal to dh by d eta. Okay. This is the transformation I am taking. So, and I am taking like I am doing differentiation with respect to eta to the above equation, so that all h in this equation will become y. So, here you can write 1 minus d by d eta of 1 minus eta square. So, this I can written as d by d eta of dh by d eta plus alpha square into dh by d eta equal to 0. Since my y is dh by d eta, this equation will be transformed to d by d eta times 1 minus eta square dy by d eta plus alpha square times so this equation is nothing but our legendary polynomial equation with alpha should equal to n into n plus 1. So, that is the eigenvalue of this legendary polynomial. So, what is basically this legendary polynomial is, if you have observed in Cartesian coordinates, we will get eigenfunctions as sin n pi. Similarly, in cylindrical coordinates, we will get Bessel functions. Same way, in spherical coordinates, we will get legendary polynomials. The solution for this type of equations are already available. So, we will directly take the solution. So, that equation will become legendary polynomial if alpha square equal to n into n plus 1. Remember, this is the eigenvalue then the equation becomes d by d eta times 1 minus eta square times so this is the final form equation. This is called legendary polynomial equation. The solution for this is given by my variable y equal to C1 P1 of eta Pn of eta plus C2 Qn of eta. So, these are basically nothing but this is legendary polynomial of first kind, this is legendary polynomial of second kind. However, this legendary polynomial of second kind have a singularity at eta equal to -1 and +1. So, for that reason we are taking this C2 equal to 0. So, my final solution will be y equal to C1 into Pn of eta. So, this is my final solution for y. Okay. If you see the problem, we need to solve solution for h, we got in terms of y. So, the transformation is y equal to dh by d eta. So, if you want to convert back, it will be h equal to integral of y into d eta. But if you remember, we need to satisfy one boundary condition, which is this psi equal to 0 at eta equal to plus or minus 1. This boundary condition we have to satisfy. For that, this integral I am modifying in terms of like, so if you define your h in terms in a definite integral from -1 to eta, this satisfies your boundary condition. We will see how it satisfies the boundary conditions, and the expression for p of n is given here. So, p of n of eta is 1 by 2 power n, n factorial d by d eta power n. Am I correct? Yeah. This is the form for p of n. Okay. So, from here if you calculate, so I will do two steps. The same thing will be similar for n equal to any value. So, I am taking, if you put n equal to 0 here, so what you will get? P naught is 1, because this entire thing will be 0, 1 by 2 power 0 is 1 and 0 factorial is 1. Similarly, if you do for P1, it will be neta. So, here you can take, this is 1. So, eta square minus 1, the derivative will be 2 eta, and here you have 2 power 1, 2 cancel, and 1 factorial is 1. So, finally we end up with P1 equal to eta. Everyone clear? So, using this definition, I am calculating my h. So, you take, so this I am taking as Qn. So, this I am taking because this is aligned with your reference book Gary Lee. So, in Gary Lee, they represent this entire integral with Qn. Okay. So, now my Q0 is nothing but integral of -1 to eta. So, my P naught is 1. So, here it will be 1 d eta. If you do integration, you will get eta plus 1. Similarly, if you do for Q1, you will get neta square minus 1 half eta square minus 1. This is the form. Similarly, if you do for another steps, you will get some constant times, this will be there. So, if you observe here, so our boundary condition is eta equal to 1, at eta equal to plus or minus 1, this will be 0. So, from here you can take h equal to 0 at eta equal to plus or minus 1. So, if you put eta equal to plus or minus 1, this is satisfying, and all higher terms you have this eta square minus 1, it will be satisfied. But if you take Q naught, for eta equal to minus 1 it is satisfying, but eta equal to plus 1 it is not satisfying. So, in our solution we will neglect Q0, means the n value should start from 1, not from 0. This you should remember. Okay. N value should start from 1 means this q naught is not an eigenfunction for our problem. So, if you do the everything, my solution will be Hn equal to Qn, where n greater than 0 or n greater than or equal to 1. This you should remember, because all n other n equal to 2, n equal to 3, n equal to 4 all are eigenfunctions of a problem, we have to consider all of them. Okay. Here if you observe that what is eta, we took eta equal to cos theta, right, in our transformations initially when you are converting e square. If you substitute eta here, what you will get? Half minus sin square theta. Everywhere you will get sin square theta. So, at the end only the first terms will be contribute, all other will be 0. If you see here, it will be half sin square theta and the other function will be r of r, that does not contribute any eta value. That is why in the solution we assume f of r, some function of r, we do not know what is that function, but the theta dependency will be sin square theta only. That is why in Stokes flow problem we took directly solution as psi equal to f of r times sin square theta. We will show why all other higher terms didn't contribute. You understand why we have taken f of, so that is direct way. So that is like once everything solved, for easiness people have taken directly f of r times sin square theta, but normally telling you have to solve this entire method of separation of variables to get that final form of the solution. Everyone clear till this part? So we find Hn, now we will find r. So the equation for r is r square d square r by dr square minus, so this alpha I am directly writing n into n plus 1. So this equation is nothing but Cauchy-Euler equation. So these type of equations have solution r equal to r power s. If you substitute this solution in the equation, it will give you one characteristic equation. If you get roots for that characteristic equation, means this solution is the solution for this equation. Okay, we will see what will happen. So if you substitute this r of s in this form, r square times, so r of s derivative 2 times derivative will be s into s minus 1 times r power s minus 2, this derivative minus n into n plus 1 times r power s equal to 0. If you see, there is one r square and this is r power s minus 2. So this will become, if you take common r power s, here r power, so this will contribute to r power s, and here also we have r power s. So if you take r power s common, you will end up with s into s minus 1 minus n into n plus 1 equal to 0. This r power s cannot be 0. If it is 0, you will get trivial solution. We do not want trivial solution. So we want solution which is not trivial. So we should equal this part to 0, not this to 0. Understand everyone why we are not equating r power s to 0? If we equate this to 0, we will end up with r equal to 0 is the solution. But we want some unique solution, so we are equating this to 0. So this will be s square minus s minus n square minus n equal to 0. So this is nothing but a quadratic equation. We know the solution of quadratic equation. So the solution for this is s equal to, so if you take a x square plus bx plus c equal to 0, so the solution will be minus b plus or minus so this is the solution for quadratic equation. So if you substitute that, you will end up with plus 1 plus or minus 1 plus 4 into n square plus n by 2. So, this is what you will get. So, if you simplify this expression, so this part, this inside the square root will be 1 plus 4n square plus 4n. This is nothing but 2n plus 1 whole square. Okay. So, this becomes 2n plus 1 whole square. So, root and square will get cancelled. You finally end up with expression like this. So, if you do that math, you will have n plus 1 and minus n are the roots. So, we have a unique solution. So, my r will be some constants, what I use, a dash. So, this is my solution for r, Rn. Similarly, Hn is Qn, right. So, my final solution will be omega equal to summation of n should run from 1, because I already told why it should run from 1, not from 0 to infinity. So, this will be our solution. So, final solution of omega will be n equal to 1 to infinity a n dash r power n plus 3 plus c n dash r power minus n times Qn. So, this is the solution, this is the final solution. This is solution for what? This is solution for e square omega equal to 0. Okay. This is the solution for e square omega equal to 0. Now, we will solve the other equation. What is the other equation? Other equation is e square psi equal to omega. Oh, n plus 1. Okay. See, this omega is same as whatever we have obtained here. If you see this equation, it has minus. It does not matter because it will be observed in the last. So, this is the equation. So, if you see this equation, this has homogeneous part and one non-homogeneous part. To solve this, we have to split into homogeneous solution plus particular integral, whatever we have seen there. So, my psi equal to psi h plus psi p. If you split your equations, you will get e square psi h equal to 0 and e square psi p equal to minus omega, right. This equation is same as this equation, but the variable is different, that is it. This omega you can take any variable, same. So, for this equation phi h also the solution is in the form of this. You understand? The equation is the form of the equations both are same here and for omega. So, I am taking omega h is same as this equation with different constants, same, that r dependency is same, n plus 1 and minus n. So, now we will see particular integral, that e square omega. So, if you observe this equation e square psi p, so that whatever minus it will be observed in constants, that constant again will be a new constant. Okay. So, this is the solution, that E square P equal to minus omega. This omega, this is the omega, same omega, this is the particular solution. Now, if you have observed, our homogeneous solution has same Qn dependency, particular integral also you have Qn dependency, and this is a function of r power lambda. If you see some power, you can say some power, this form, this is r power some x, like r power lambda. Same Qn dependency in particular integral, same Qn dependency in homogeneous solution also. So, now I am taking my solution is in the form of sigma p into Qn. Okay. So, this is my form. So, this has to satisfy this equation. So, if you substitute in E square, this E square of r lambda times Qn. So, we should need this Qn dependency. So, this Qn basically are recursive, there are recursive relations. You can write like Qn dash is some function of n times Qn, like this you can write as a recursive relation. This E square, if you do all the math, you will finally end up with some k of n comma lambda times r power lambda minus 2 Qn. Why this is r power lambda minus 2? Because it is E square, dou by dou r square. So, 2 will be minus from the solution r power lambda. You understand this step? This can be written in simple form. So, this can be in some constant in terms of n and lambda. If you substitute everything, you can take these two terms as a common, and whatever left will be kn of lambda. Okay. This should satisfy the right hand side, right? Whatever this is what your left hand side. So, this should equate to your right hand side. So, this kn lambda r lambda minus 2 Qn. So, I am considering single term contribution. So, first I am considering this term contribution. So, if you take that term contribution, when these two terms should be equal, this should be an dash and this power should be equal, right? Then only both terms can be comparable. So, from here kn should be some this constant, and lambda minus 2 should equal to n plus 1. Understand? Now, this lambda will becomes n plus 3. Similarly, if you do for the other term, you will get lambda minus 2 equal to minus n. So, this will give you lambda equal to 2 minus n. So, your particular integral will be phi p is equal to, we already used b and c for homogeneous function. So, I am using a n r power n plus 3 plus c n r power 2 minus n. Okay. How I got? So, this is the final form we will get, phi p the same. So, this is the homogeneous equation, I mean solution for homogeneous and solution for particular integral. What is the solution for our psi? Psi is nothing but psi p plus psi h. So, we have to add both. See, if you can see both have Qn dependency, you can take common, and your final solution in the form of So, this is your final solution for stream function. Everyone clear till this part? So, this is the solution, but we do not know whether it is correct or not. When we will get, we have to apply our boundary conditions so that it will become exact solution for our problem. Everyone clear till this part? Now we will go to applying boundary conditions. So, I am erasing this part also because I need to do two fluid. So, this is the solution for psi for the equation, like you can split the combine the equation, it will be e power 4 psi equal to 0. If you remember, our inner fluid and outer fluid have same equation. So, the solution form is same for inner fluid and outer fluid, the same form for inner fluid and outer fluid, but different constants. Got it? So, now we will apply boundary conditions. So, my solution for inner, so inner will be represented with caret, outer will be without any caret. So, psi n equal to 1 to infinity a power n r power n plus 3 plus b power n r power n plus 1 plus Cn r power 2 minus n plus Dn r power minus n Qn. So, similarly you can write for outer fluid psi equal to n equal to 1 to infinity An r power n plus 3 plus Bn r power n plus 1 plus Cn r power 2 minus n plus Bn So, these are the final forms for two solutions. This is inner fluid, that is outer fluid. Now, we will apply boundary condition. The first boundary condition we are applying is far field boundary condition. If you remember the far field condition, this psi as r tends to infinity, it will be half r square into 1 minus eta square. This will convert into q. If you remember, our q1 is nothing but 1 by 2 eta square minus 1, our q1. So, this can be converted to minus r square q1, right, this. So, this is the final form in terms of q1. Why I am converting, it will be easy to solve. Now, if you see, when r tends to infinity, which terms will goes to infinity first? If you put n equal, for example, if you put n equal to 1, this will be r power 4, this will be r square, this will be r power 1 and this will be r power minus 1. You take a simple example, suppose you put r equal to some 100. So, this value is like, I am erasing this part. If you take r equal to some 100 or 1000, because it is, so this becomes 10 power 12, this becomes 10 power 6, 10 cube and 10 power minus 3. Comparing to all these numbers, these two numbers are very big, right. If you compare with, this is 1000, this is 1 million, this is higher than that, 1 billion. If you compare with all these numbers, these two terms will become infinity, faster, much faster compared to other two terms. That is why, since our solutions need to be bounded, not to be unbounded, we are omitting this an and bn. Okay. However, so the thing is, an will be 0 for all n values, but if you see our condition at infinity, we have r square dependency. So, in all of this, so our n starting with n, this is the least. If you see all the things which has r square, b has r square, and if you take n equal to 2, it will be r cube, we do not need. So, we have to keep b1 so that it will align with our boundary condition. Okay. So, for that reason I am taking, so if you similarly bn also 0 for n greater than equal to 2. You understand why greater than or equal to 2? Because we need to keep our r square dependency. If you put n equal to 1, it will be q1 and this will be r square. If you compare with this equation, this b1 should equal to minus 1. So, this goes to 0, this goes to 0, and we cannot comment on other Cn and Dn. Oh, this analysis should be here. Okay. Because this is outer fluid, this is inner fluid. Everyone clear with this step? So, with this step my equation will become phi equal to minus r square q1 plus summation n equal to 1 to infinity Cn r power 2 minus n plus Bn r power minus n into Qn, if you remove all a and bn's. Okay. And similarly we have boundary condition at r equal to 0. At r equal to 0, psi should be found bounded. So, if you see this equation, these will be 1 by r's, C1, Cn and Dn, this. So, this will make my solution goes to infinity. Since my solution want to be bounded, here this Cn tends to 0 and Dn tends to 0. Understand? This will be numerator. If you put 0 also, it will be 0, but here it will comes to denominator. 1 by 0 becomes infinity, it is unbounded, but I want my solution to be bounded. So, I am making Cn and Dn equal to 0. So, from here you will get psi cap equal to sigma n equal to 1 to infinity a n r power n plus 3 this is the final form of equations. From here I will use PPT because we will have derivatives, it will become more complex to write on the board. So, this is the final form of solutions. One is for left side is for inner fluid and right side is for outer fluid. Okay. So, for finding other constants, we need to apply boundary conditions at fluid-fluid interface. What are the fluid-fluid interface conditions? These are not conditions. So, here I am calculating all the derivatives at r equal to 1, so that we can directly use in the next steps. Okay. So, these are the derivatives calculated at r equal to 1. The first condition is no slip condition, which is nothing but tangential velocity should be equal. If you converted that into stream function, you will get this form, dou psi by dou r equal to dou psi cap by dou r. Okay. So, if you take the expressions from the earlier slide, you will end up with this expressions. If this to be true, this like that equation should will be true only if all the coefficients of Qn should be equal. Then only the equation will be satisfied, otherwise it will not be satisfied. Since we have explicit for Q1, so I am splitting my equations into two parts. I am comparing Q1 coefficients and all other Qn coefficients. Clear? Since I have Q1 explicitly from the summation, that is why I am taking Q1 coefficient separately, all other n coefficients separately. If you take like that, this is the Q1 coefficients. If you rearrange, this will get this form. Similarly, for n greater than 2, if you do simplification, you will get this forms. So, this is the final equations. These are one set of equation. Similarly, this is no slip. Now we will apply no penetration condition. This is no penetration condition. If you apply, you will get this form. Same approach here. I am taking q1 dash coefficients and qn dash coefficients. If you do so, so these are the coefficients for q1 dash and qn dash. Similarly, other boundary, because V r equal to 0 for both inside and fluid and outside fluid. If you apply, you will get this set of equations. If you have doubts, you can come to us, we will explain. Now we have a continuity of tangential stress condition. This is these all things you have to sit and solve, otherwise you won't understand. Or you can use Mathematica or MATLAB, but better you solve with your hand so that you will get better understanding. Similarly, here also, if I compare, I will get the set of equations. So at the end, for n equal to 1, these are the 4 equations I will get. These are system of linear equations. If you solve these equations, we will get the solution. So when so this equation might have solution, may not be, it might have or might not have. So to find out that, I am writing this in a matrix form. When solution will be possible for Ax equal to B system, det of A should not be equal to 0, because otherwise inverse won't exist for a square matrix. So this is Ax equal to B. So if you calculate det, you will get this det expression. So this det expression will not be 0. So you can find x by using this A inverse into B. So if you do so, you will get expressions like this: A1, B1, C1 and D1. Similarly, for equations n greater than or equal to 2, if you write in this form, it will be like this. So here also det won't be 0, but the thing is, here the B matrices all are zeros. Even if A inverse exists, since my B is 0, all x will be 0. That is why for n greater than 2, all coefficients are 0. Now you will recall when I told in the H equation solution, only q1 is exists, all other qn are vanished. That is why in the Stokes flow over a sphere problem, we directly assume our solution is f of r times sin square theta. That sin square is nothing but q1. You understand why we are taking this? Is the full process you have to do, then only you will get the final form. So if you are doing all these things, if you substitute these equations, you will finally end up with expressions for psi. Our aim is to calculate velocity fields. So using this psi, we can calculate velocity fields using the definition, this definition Vr and V eta. If you put psi expression here, you will get inner fluid, outer fluid things. So this is the final form. Everyone understand? So these are the expressions for, you can actually validate these equations also. You have boundary conditions, right? So always you should validate your solution, because you got some solution. It might be right, it might not be right. Always you have to check with your boundary conditions, whether the boundary conditions is satisfying Vr and V theta or not. And one more thing, continuity equation also you can try to verify this equation. And similarly, for calculating drag force. Yes sir. So simply I am saying this is drag force and drag coefficients. So from here you can show that. So what is our lambda? Lambda is nothing but viscosity ratio, inner by outer. So if inner viscosity is very high, means it resembles solid. So when lambda tends to infinity, these equations should match with your Stokes flow over a solid sphere. So if you do that, you can see the F drag force 6 pi mu u infinity a, that is what your drag force in your Stokes flow. Similarly, the drag coefficients 24 by Re. So these are the checks you have to do, make sure your solution is correct. So if you plot your Vr and V theta, so these are the internal circulations you will get if you plot that Vr and V theta. You can see here how the fluid is moving inside. This will enhance your micro and macro mixing, which will help in distribution, homogeneous distribution of reactions and all. And if you want to compare, so this is one plot, so this is temperature contours. So this is the same system, the whatever the red color initially tau equal to 0 will be your drop or solid sphere. So the top one represents the solid one, the bottom one represents the fluid sphere with the same properties. So this is here what basically happens is the red is hot sphere or hot solid sphere. So if you see as the time passes how the heat is distributing to the content. If you see when, so these both are plotted for same time things. If you see in the solid sphere, the heat distribution is less. If you see in the fluid sphere case with internal circulations, at the same time this is already become cold, but here still hot, means here the thing is the internal because of internal circulation, here the rate of heat transfer is very fast. So this is one of the application of this. This I can conclude this. Thank you everyone.